Today we are going to discuss on a topic which is very much attached with the sustainability in iron making, and that is hydrogen injection in place of PCI in blast furnace iron making. So welcome to this presentation on a transformative idea, what I just spoken. Can hydrogen replace PCI in the blast furnace? So in this session, we will explore the technical insights from a research study. We are talking about a research study recently done in 2023 using a detailed modeling and analysis to understand how hydrogen injection affects blast furnace operation, stability, and emission. Now, coming to a questions, why hydrogen in blast furnace? And it is very obvious that steel making is one of the largest industrial contributor to CO2 emissions globally. In integrated steel plant, the blast furnace accounts for majority of those emissions, while pulverized coal injection or PCI has helped reduce coke usage. So it's still carbon based and emit CO2. This is where hydrogen comes in, and it's a clean reducing agent that forms only steam. The big question is, can we inject hydrogen through the tuyeres instead of coal and still run the furnace reliably? So this is a really challenge, and for this study outcome is very important. Now let's see what this study aims to do. This study focuses on one goal, which is about determining the maximum hydrogen that can be injected to replace PCI without compromising the furnace thermal or operational stability, because stability is all important when we started putting hydrogen. It looks specifically at key parameters like flame temperature, top gas temperature, and internal reaction condition. These three factors becomes very important. So simulation were used to predict not just process changes but also the impact on emissions. The study assumed that coke rate and hot metal productivity are kept constant. Now coming to the methodology of the execution part of this project. So methodology in simple term, we can say that this is about a research on two modeling tools. One is heat and mass balance model to understand the energy and gas flow inside the furnace. And secondly, a 2D global blast furnace model simulated the internal behavior like gas composition and the reduction of iron ore across the furnace cross section. So this together activity, this both activity together, they provide a detailed understanding of how hydrogen behave inside the blast furnace. Now coming to the matter of the constraint and the the two key parameters were monitored uh, as a constraint matter. One is raft and other is top gas temperature. The raft need to stay high enough for efficient combustion, as all blast furnace people know, and at the same time top gas temperature should not fall below around 100 and less than that to avoid these dew point issues. Initially oxygen is injected to keep flame temperature stable, but once top gas temperature hits its limit, that is what about 100 degree, any more hydrogen injection forces raft to drop further. And this is a challenge within a safe limit of around 180 degree. So this stage a constrained approach helps ensure self operation. So it is a challenge to keep the flame to the limit. At the same time, we have to keep our top temperature also within the range. Now coming to the how much hydrogen can be used. The maximum safe injection rate was found to be 19.5 kilograms of hydrogen per ton of hot metal. At this level, PCI is reduced to 37.5 kilogram per ton. Importantly, the productivity of furnace remains unchanged. It is around 7748 tons per day, which is assumed, and this parameter kept fixed. To support this hydrogen rate, we would need about 151 ton of hydrogen per day, a significant scale if we compare with the production figure. So now coming to the direct emission reductions. So how much CO2 does this save? This is also a very important question. The base case with the PCI emit about 1.16 ton of CO2 per ton of hot metal. Now with hydrogen injection, this dropped down to 1.053 tons, that is 9.5% reduction in direct blast furnace emission. This estimate assume that hydrogen used is completely green, making the things more comfortable. Now coming to the source of hydrogen, this is also very critical. Not all hydrogen is equal when it comes to the emission, and especially green hydrogen made using renewable electricity gives the best result, cutting emission by 9.5%. Now let's have some focus on blue hydrogen, which is made from natural gas with carbon capture. It still reduces emission, but by a smaller, that is 6.4%. If we consider about grey hydrogen made without carbon capture, actually increase emission. So by this technology, to truly help the environment, the source of hydrogen must be green or blue. So while performing, this is also a lesson for a courses that are to be taken into consideration while executing the project, that what type of hydrogen we are using. Now let us see, can hydrogen complete the compete the economically? From a hydrogen perspective, PCI currently costs around $165 per ton. To break even, hydrogen would need to be priced around $370 per ton, much lower than today's green hydrogen prices, which are around $5,000. So future price drop could bring green hydrogen down to $1,000 per ton. And even then, we need carbon pricing or carbon credit of about $120 per ton of CO2 to make it economically viable. So we can see that what is the challenge is all about. It is a very complex and it is challenging. Now coming to the what happens inside the furnace when this hydrogen pass on. The internal furnace behavior also changes with the hydrogen injection. The reduction of iron oxide occurs faster, that everyone knows, and earlier in this furnace, meaning the cohesive zone seems a more rapid transition to metallic iron. This improves gas solid contact and may enhance furnace efficiency. It also reduces the depth of cohesive zone, potentially making burden descent smoother. So many activities are there, and while executing the hydrogen projects, these things are to be very carefully studied. Now coming to the low hydrogen utilization challenge, we can say that this is one of the biggest challenge, especially when hydrogen is getting injected in the blast furnace. Even at a maximum injection level of only about 50% of hydrogen reacts inside the furnace. This is the best value. The rest exit with the top gas. In real world trials, hydrogen utilization was even lower, as low as 32 to 40%. To improve this, the study suggests options like top gas recycling and modifying how hydrogen interact with the burden. So, the important thing is, what are the key takeaways? So, we can summarize these projects in this way that yes, hydrogen can safely replace up to 19.5 kilogram of PCI per ton of hot metal. This leads to 9.5% drop in CO2 emission while maintaining furnace productivity. However, hydrogen utilization is relatively low and current hydrogen costs are too high for widespread adoption. But with the right technology improvement and policy support, hydrogen injection could play a vital role in green steel making. So now coming to what next? So looking forward, we need to scale up hydrogen production and reduce its cost. Blast furnace may need redesign to improve hydrogen utilization. For example, using top gas recycling or hybrid shaft BF system. We can also combine hydrogen with oxygen enrichment and bio-based injectant. Digital optimization and carbon pricing will be a key enablers. Together, these steps can pave the way for a truly low carbon future for iron and steel.